Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage. This is a acid base equilibria question that was asked on a multiple choice in an older AP Chem exam, and we're going to learn a lot from this. This is really an excellent question. One of the things I like about the AP questions, especially the MC ones, is that you can learn a lot just by seeing what they want you to answer. They go to the heart of a lot of chemistry. So here we've got a situation where we've got 3 Erlenmeyer flasks, and they have in them an acid solution that was made using a pure solute, in this case hydrogen fluoride, which when dissolved is called hydrofluoric acid, and hydrogen chloride, which is the solute, when dissolved makes hydrochloric acid, and this, I hope you remember, is the ammonia molecule, and we've got an ammonia solution when it's dissolved. Now, they tell us a little bit about these. Oh, by the way, of these, HCl and ammonia, the hydrochloric acid and ammonia solutions, you're going to find in most labs, high school labs, college labs. People work with it all the time. The hydrofluoric, though, is very, very dangerous. In fact, you wouldn't want it in a glass flask because it reacts with glass, and it's also extremely toxic. Don't work with hydrofluoric acid or hydrogen fluoride for that matter without having a lot of training in terms of safety, all sorts of safety gear, and antidotes, because it's a horrible poison. If you don't get the antidote for it quickly, you're unfortunately doomed. And so don't work with hydrofluoric acid. Have your lab partner work with it. So let's go to the question. They tell us some other stuff. They give us the pHs of the 3 solutions. Here we have a pH of 2, pretty high hydrogen ion concentration, 10 to the negative 2, 1/100th molar hydrogen ions or hydronium ions. And the same thing for the hydrochloric acid. And then we've got our ammonia solution here with a pH of 12, quite alkali. We've got 400 mLs of each of these, the same volume, and they tell us a little bit about the strength of the acids. You should know that hydrochloric acid is a strong acid. It's presumed that an AP student would be able to recognize that. Strong acid. And then here we've got ammonia, which is a weak base, and then here we've got hydrofluoric acid, a relatively weak acid. Now here's their question. Which solution has the greatest number of ions? And which solution would neutralize the most sodium hydroxide? And they give you your choices, either one of these, and then they've got a choice of them all neutralizing or being the same. So let's go to this diagram that I have, where we've got these things, and here are our solutions, again, all having the same, both of these have the same pH, being acidic. Now, on those questions, we would know that this ammonia wouldn't neutralize sodium hydroxide. This is basic. So for the question that was asked about the neutralizing sodium hydroxide, these two would be the possible choices. But again, let's examine these in terms of what's really happening. It looks like both the hydrofluoric and HCl are pretty much the same. They have this pH rating, the acidity rating of 2, 1/100th molar hydronium ions, this stuff that's really nasty for acids. And that means that we've got a certain number of hydronium ions, hydrogen ions here, with the A-. This HF breaks up into H plus and A-. And because they have the same pH, they're going to have the same number, in this case, this diagram of H pluses. So they're going to be equal in that case. Now, in the case of ammonia, we have it reacting with water to pick up an H plus. So we've got NH3 and an H plus, NH4 plus, which would be the ion here, and we've got the hydroxide ion here. Now, with a pH of 12, it means it's POH, is hydroxide ion concentration, is POH of 2 means 1/100th molar hydroxide. So if we're looking at things, this ammonia ionizes to make these 2 ions, and we know that they're both going to be 1/100th molar each, and 1/100th molar, 1/100th molar. We're going to have the same concentration of ions. So even though this is a weak acid, even though this is a strong acid, and even though this is a base, in terms of electrical conductivity, ions that can move, they really have the same concentration of ions. In this case, the ions are a bit different because we know this has a pH of 2. pH and pOH add up to 14 at room temperature under standard conditions. So we've got these concentrations of, oh, this is wrong here. This should be the hydroxide ion concentration is 10 to the negative 2. The hydrogen ion concentration here is at 10 to the negative 12. The hydroxide reacts with hydrogen ions and suppresses them. So this is wrong. I should have said the hydroxide is 10 to the negative 2. So our first question is answered. They have the same ion concentration. And again, ignore this incorrect statement. And that answers our first question. Now, the second question is, which of these can neutralize the most sodium hydroxide? Now, hydroxide is a strong base. It will react with any acid. And of course, we've eliminated our ammonia, which already has hydroxide. So let's go a little bit further and look at what's really in these two solutions. These, I should say, all three solutions. And this is where we get into difficult and AP level chemistry for acids and bases. This is a weak acid. And in order for it to have a pH of 2, you had to dump in a lot of this acid. That makes this hydrofluoric acid solution really dangerous because you've got hidden in here HF, HF, HF waiting, because only a few of these at any given time will produce H+, and of course then the H+ will combine with the F- and come back again. This is a dynamic equilibrium. And so within here, this weak acid, in order to get a pH of 2, we had to dump in a lot of it. That makes it a bit more dangerous because you've got actually more acid in this pH of 2 than you have of this acid here. In this case, the HCl is a strong acid. It 100% ionizes. There's no leftover HCl. When they made this, they didn't need much hydrochloric acid because it's a strong acid. In fact, here's the concentrations that they used to make up these solutions. I did the calculation doing the equilibrium expression. And in order to make this pH of 2, we need 0.16 molar hydrogen fluoride. So there's lots of HF here, making a little bit of H+ to a pH of 2. In order to get the same amount of H+, pH of 2, we only needed 100th molar HCl. You could almost wave the bottle of hydrochloric acid above the solution to get this pH of 2. You don't need much strong acid to get low pHs. You need a lot of weak acid to get these low pHs. So in the end, we have the same level of, if you like, acidity for both of these, but hidden in this, there's a lot more acid. So it's ironic that the weak acid can be more dangerous than this acid because it will only take, oh, by the way, here's the amount that's in here. Of the 400 mLs, we have 64 millimoles of hydrogen fluoride molecules. In this case, this is how many were used to make this solution. In this case, we use 4 millimoles of HCl, but they're all used up. There's none left. And the H+ concentration is quite small in this 400 milliliters. And of course, this is even a weaker base, and we've got ourselves 2.2 moles of ammonia. We have 2,200 millimoles of ammonia present in this solution that's got a pH of 12. In the end, you'll be able to neutralize 64 millimoles of sodium hydroxide with this weak acid because we had a lot of it in there. But you could only neutralize 4 millimoles of sodium hydroxide with the HCl because there isn't much acid in there. And of course, if we were a neutralized acid, we would end up having to have 2.2 moles of HCl here. So there we go. Let's go back to our question. And here you can see where it's such a clever question where they say, oh, a student looking at these must all, these have 2s, these have 12s, you might guess ammonia. This has a lot of chemistry in it. There's important things in dealing with the strength of the acids, whether they're an acid or a base, the idea of pH, the idea of pOH. This is a question that requires a lot of knowledge. So, as I say, I respect these MCs because in order to get these right, unless you guessed, you had to know a lot of acid-base equilibria. Okay, that's it. MCs forever.